Imagine building a wall, not to stop an invading army, but to stop the ocean itself. A barrier stretching nearly 400 kilometers, built to confront one of nature's most destructive forces. Many people know about China's Great Wall. Almost no one knows about Japan's. Yet every day, it stands silently between millions of people and the Pacific Ocean.
Every civilization leaves a mark. These are the echoes of power.
When most people think of tsunami protection, they imagine evacuation plans, warning sirens, emergency shelters. But after one of the most devastating natural disasters in modern history, Japan concluded that warnings alone were no longer enough. Engineers faced an impossible question. How do you defend hundreds of kilometers of coastline against waves carrying the force of entire buildings? The answer wasn't one giant wall. It was an integrated coastal defense system. Massive reinforced seawalls, floodgates, breakwaters, earth embankments, drainage systems, and carefully designed evacuation infrastructure, working together as one. Today, this network stretches across large sections of Japan's northeastern coastline, making it one of the most ambitious coastal engineering programs ever attempted. But this isn't simply the story of concrete. It's the story of how engineers tried to redesign an entire coastline to survive the next tsunami. For centuries, Japan has lived with earthquakes, and wherever powerful earthquakes occur beneath the sea, tsunamis are always a possibility. Unlike ordinary ocean waves, a tsunami doesn't begin as a towering wall of water. Out in deep ocean, it may pass almost unnoticed, but as it approaches shallow coastal waters, everything changes. The wave slows, its enormous energy compresses, and the water rises dramatically. Within minutes, entire coastlines can be overwhelmed. Traditional seawalls had existed in Japan for decades. Many successfully protected communities from smaller storm surges and moderate tsunami events. But engineers discovered an uncomfortable truth. Designing for average disasters doesn't prepare you for extreme ones. Some coastal communities experienced tsunami heights far beyond what older infrastructure had been designed to withstand. Entire neighborhoods faced forces that exceeded previous engineering assumptions. The challenge wasn't simply building a taller wall. A taller wall creates greater structural loads. It requires deeper foundations, stronger reinforcement, more complex drainage systems, and careful consideration of how overtopping water behaves if waves exceed the wall's height. Engineers also had to balance safety with daily life. These weren't isolated military structures. They would stand beside fishing ports, roads, homes, schools, and entire communities that depend on access to the sea. Every section required different engineering solutions based on local geography, coastline shape, expected wave energy, soil conditions, and surrounding infrastructure. Instead of constructing one continuous identical barrier, engineers designed hundreds of individual coastal defense sections, each optimized for its specific environment. Because the real challenge wasn't simply stopping water. It was understanding exactly how the ocean behaves before deciding how to resist it. And that understanding would lead engineers to one remarkable realization. The strongest wall in the world means nothing if its foundation cannot survive the first wave. Stopping a tsunami isn't as simple as building a taller wall. In fact, height alone can create new engineering problems. When a massive wave crashes into a vertical surface, the impact force is enormous. Thousands of tons of moving water strike the structure within seconds. If that energy isn't managed, the wall itself can fail. Japanese engineers approached the problem differently. Instead of treating the seawall as a simple barrier, they designed it as an energy management system. Many sections feature reinforced concrete walls supported by deep foundations extending into stable ground beneath the coastline. These foundations prevent the wall from sliding, tilting, or being lifted by the tremendous hydraulic forces generated during a tsunami. The front face of the wall is carefully engineered to resist repeated wave impacts. Behind it, compacted earth embankments help distribute loads while providing additional structural support. Drainage systems are built directly into the design, because water doesn't only push against the front of the wall, it can also seep beneath it. If underground water pressure builds up, the foundation itself becomes vulnerable. Engineers installed drainage layers and pressure relief systems to reduce this hidden threat. Every meter of the structure was calculated not only for strength, but for stability over decades of exposure to earthquakes, saltwater, and severe coastal weather. Because the wall wasn't expected to survive one tsunami, it was expected to survive generations. Yet even the strongest wall has limits, which led engineers to another important realization. Sometimes, you don't stop the wave, you slow it down. One enormous wall may sound impressive, but modern coastal engineering rarely relies on a single line of defense. Instead, Japan adopted what engineers call a multi-layered protection system. Think of it like a series of shields. If one layer reduces the wave's energy, the next layer has less force to withstand. Offshore breakwaters form the first barrier. Positioned away from the coastline, these massive concrete structures interrupt incoming waves before they reach land. As waves pass over or around them, part of their energy is dissipated. Closer to shore, the seawall becomes the second line of defense. Its purpose isn't always to stop every wave completely. Instead, it reduces flooding, slows water movement, and buys valuable time for evacuation. Behind the seawall, engineers often constructed elevated roads, earth embankments, and flood-resistant landscapes that act as additional protective layers. Even buildings themselves are considered part of the defense strategy. Critical facilities such as hospitals, emergency centers, and evacuation shelters are frequently located on higher ground or designed with reinforced structures capable of withstanding severe flooding. The philosophy is remarkably simple. Never depend on one structure, because nature eventually finds weaknesses. But overcoming multiple engineered barriers requires far more energy, and every second gained can save lives. Still, even the most advanced defense system must confront another reality. Japan experiences more than tsunamis. It also experiences powerful earthquakes. Most coastal walls around the world are designed to resist waves. Japan's seawalls face another challenge. The ground itself can move. Powerful earthquakes generate intense shaking that places enormous stress on foundations, retaining structures, and reinforced concrete. A wall that survives the tsunami must first survive the earthquake that creates it. Engineers therefore designed many seawall sections with deep pile foundations anchored into stable geological layers beneath softer coastal soils. These foundations improve resistance against settlement and lateral movement during seismic events. Expansion joints are incorporated into long stretches of the wall, allowing controlled movement as the ground shifts. Instead of forcing the entire structure to behave as one rigid block, engineers divided it into carefully designed segments. Reinforcing steel inside the concrete increases ductility, allowing the structure to absorb energy without failing suddenly. Advanced geotechnical investigations also determine where additional ground improvement is required before construction begins. In some locations, engineers strengthen weak coastal soils to reduce the risk of liquefaction, a phenomenon where saturated ground temporarily loses its strength during strong earthquakes. The result is a coastal defense system designed to withstand two disasters occurring within minutes of each other. First, the earthquake, then the tsunami, and after construction was complete, the engineering challenge didn't end. Because protecting hundreds of kilometers of coastline requires something just as important as construction: constant monitoring and maintenance. Building hundreds of kilometers of seawalls was only the beginning, because no matter how strong the structure, it must know when the ocean is coming. A tsunami can travel across the Pacific Ocean at speeds approaching that of a commercial jet. By the time people see the wave, it may already be too late. So Japan built something equally important as the wall itself: an invisible monitoring network. Far offshore, seafloor pressure sensors constantly measure tiny changes in ocean pressure. A tsunami passing overhead may only raise the sea surface by a few centimeters in deep water. But those small pressure changes reveal the wave's presence long before it reaches land. The data is transmitted through underwater communication systems to surface buoys. From there, information is sent almost instantly to monitoring centers across Japan. At the same time, hundreds of seismic stations continuously detect earthquakes beneath the ocean floor. Powerful computer systems rapidly estimate the earthquake's location, depth, magnitude, and the likelihood of tsunami generation. Within minutes, engineers and emergency agencies receive detailed forecasts predicting expected wave heights and arrival times along different sections of the coastline. The seawall itself doesn't decide when danger is approaching. An entire digital network does. Because in modern coastal engineering, the first line of defense isn't concrete. It's information. Yet even perfect warnings can't stop the ocean. When a tsunami arrives, another engineering system immediately begins working. Japan's coastline isn't made up of uninterrupted seawalls. There are fishing harbors, river mouths, shipping channels, road crossings, places where openings are unavoidable. Every opening creates a weakness. Engineers solve this problem with another remarkable invention: massive tsunami floodgates. Under normal conditions, these gates remain open. Fishing boats leave the harbor. Ships enter ports. Rivers continue flowing into the sea. Daily life continues uninterrupted. But when tsunami warnings are issued, everything changes. Hydraulic systems activate. Gigantic steel gates begin closing across harbor entrances and flood channels. Some gates rotate upward from beneath the water. Others slide horizontally across navigation channels. Some rise vertically like enormous steel walls. Each design depends on the local geography and water conditions. These structures must operate quickly, reliably, and often under extreme weather conditions. Backup electrical systems ensure operation even if the primary power supply is interrupted after a major earthquake. Engineers also designed many floodgates to resist debris carried by incoming waves. Shipping containers, fishing vessels, vehicles, and broken structures can all become dangerous projectiles during a tsunami. The gates must survive not only water pressure, but the impact of whatever the ocean carries with it. Yet engineers understood something important. No wall, no gate, can guarantee complete protection against every possible tsunami, which is why Japan never relied on engineering alone. One of the biggest misconceptions about Japan's coastal defenses is that the seawall is expected to stop every tsunami. It isn't. Modern disaster engineering follows a different philosophy. Assume that extreme events can exceed design limits. Then prepare for what happens next. Entire coastal communities have been redesigned with this principle in mind. Critical facilities such as hospitals, emergency operation centers, schools, and evacuation shelters are often located on elevated ground or constructed with reinforced structural systems. Clearly marked evacuation routes connect neighborhoods to higher elevations. Pedestrian bridges, emergency stairways, and vertical evacuation towers provide additional escape options where natural high ground is limited. Road networks are also planned to improve emergency access after disasters. Some coastal forests have been restored to reduce erosion and help slow smaller waves before they reach developed areas. Public warning systems, mobile alerts, sirens, and electronic information boards work together with engineering infrastructure to guide people towards safety. The result isn't simply a giant wall. It's an integrated resilience system where civil engineering, urban planning, emergency management, and public education operate as one coordinated defense. Because Japan's greatest lesson wasn't that engineers can defeat nature. It was that the safest communities are built when people and engineering prepare together. But after investing billions of dollars and transforming hundreds of kilometers of coastline, one final question remains. Has Japan's Great Wall against the ocean truly changed the future of coastal engineering, or is it a solution only one nation could build? When Japan began constructing hundreds of kilometers of tsunami defenses, The world watched. Some engineers called it visionary. Others questioned whether walls this large could ever justify their cost. After all, concrete alone cannot eliminate natural disasters, and no engineering structure can guarantee absolute protection against every possible tsunami. So, was it worth it? From an engineering perspective, the answer isn't measured by how many waves the wall stops. It's measured by how much risk it reduces. Every meter of seawall lowers the force reaching communities behind it. Every floodgate delays incoming water. Every elevated road provides another evacuation route. Every additional minute gives emergency responders more time to act. Modern disaster engineering isn't based on perfect protection. It's based on reducing consequences. Japan's coastal defense program also transformed engineering research around the world. Countries vulnerable to tsunamis, storm surges, and rising sea levels now study many of the same design principles. Multi-layer coastal protection, performance-based engineering, resilient infrastructure, integrated monitoring systems. Rather than relying on a single massive barrier, engineers increasingly combine natural landscapes, protective structures, early warning technology, and urban planning into one coordinated defense strategy. Japan demonstrated that protecting a coastline isn't about building one extraordinary structure. It's about designing an entire system where every component strengthens the next. And perhaps that's the project's greatest engineering legacy. But the future presents an even bigger challenge, one that no wall was originally designed to face. The ocean is changing. Sea levels are gradually rising. Storms are becoming more intense in many regions. Coastal populations continue growing. That means tomorrow's coastal defenses must do far more than today's. Engineers are already designing the next generation of resilient coastlines. Artificial intelligence is beginning to analyze ocean conditions, structural health, and weather forecasts in real time. Digital twins allow engineers to simulate tsunami impacts before construction even begins. Fiber optic sensors embedded inside seawalls continuously monitor strain, movement, moisture, and temperature. Instead of waiting for visible damage, infrastructure can report its own condition. Some researchers are combining engineered structures with natural defenses, such as restored wetlands, coastal forests, and artificial reefs. These ecosystems help absorb wave energy while improving biodiversity. Future seawalls may even incorporate modular construction techniques, allowing sections to be upgraded as climate conditions evolve over the coming decades. The goal is no longer to build structures that remain unchanged for 50 years. The goal is to build infrastructure capable of adapting alongside nature. Because the coastline itself is never static, and neither should engineering be. Most walls in history were built to keep people out. Japan built one to keep the ocean back. It stretches across hundreds of kilometers of coastline, standing silently between communities, and one of nature's most unpredictable forces. Most visitors never notice the engineering hidden beneath its surface. The deep foundations anchored into coastal rock, the drainage systems relieving underground pressure, the earthquake-resistant joints, the floodgates waiting quietly for an emergency that may never come. That's the remarkable thing about infrastructure. When it succeeds, it often goes unnoticed. The greatest engineering achievements aren't always the tallest skyscrapers or the longest bridges. Sometimes, they're the structures people hope will never have to prove themselves. Japan's coastal defense system isn't remembered simply because of its size. It's remembered because it changed how engineers think about protecting entire coastlines. Not by trying to conquer nature, but by understanding it, preparing for it, and designing communities resilient enough to live beside it. This is Echoes of Power. If you enjoyed exploring one of the world's most ambitious coastal engineering megaprojects, subscribe for more documentaries uncovering the infrastructure, innovation, and engineering breakthroughs shaping our future. Because every impossible wall begins with one impossible question. Can humanity learn to live with the ocean instead of fearing it?